All right, so in this video, we're going to be talking about relations and functions. So let's first start off by defining what a relation is. So a relation is any set of ordered pairs. Okay? Now, all of the x values in the ordered pairs make up what we call the domain. So we're going to define domain as simply all the x components of our ordered pairs and then we'll define our range as all the y components of our ordered pairs. So, for example, here we could just do a really easy example and just say identify the domain and range for the set consisting of 1, 3, 2, 6, 3, 9, 4, 12, and 5, 15. So our domain, remember, are going to be all of the x components of each ordered pair. So 1, 2, 3, 4, and 5. All right. Now, put this in a little set. There we go. So now the range are going to be all of the y components. So our range is going to be 3, 6, 9, 12, and 15. Okay? Now, what we like to do with this is we will go ahead and use what we call a mapping to show a relation. So a mapping is used to show a relation. So if I use the example above, I'm going to create a circle, and I'm going to call this my domain. And within this circle is going to be all of the elements that are located in my domain for the example above. So those elements are going to be 1, 2, 3, 4, and 5. Now I'm going to create another circle, and this is going to be the set where all the elements inside this set are going to be my range. So they will be 3, 6, 9, 12, and 15. And the mapping comes into play when I draw an arrow starting from my domain and extending it into the range at the element or at the ordered pair that it kind of connects. So 1 connects to 3, 2 connects to 6, 3 is mapped to 9, 4 is mapped to 12, and then 5 is mapped to 15. Okay? Now, excuse me, this is one way that we can do this, but we can also do this using even a picture. So, example, find a domain and range for the following. All right, so I'm just going to go ahead and just do an XY Cartesian coordinate plane real quick, and we'll keep the numbers simple enough. And I'll put like a point right there. I'll do one here, here, down here, and right there. So if I have just these ordered pairs here, I can go ahead and list them all And then from there, I can go ahead and figure out what my domain and range is. So the first thing we're going to do, like I said, is we're going to list them. So we have -2, 1, -1, 0, 0, 1, 1, -2, and finally 2, 1. And if I go through each ordered pair, I can quickly find my domain by saying, well, it's going to be all the x components of the ordered pair. So it's going to be -2, -1, 0, 1, and 2. And then all my range are going to be 1, 0, and -2. Because as you can see here, we have, and I'll highlight it in blue for us. We have 1, 1, and 1, and they're all repeated. So it's only the number 1. And then we have 0 and -2. So 1, 0, and -2. And I guess for consistency, I'll put them in order. So -2, 0, and 1. So my domain and my range, respectively. And this leads us into one of the most special types of relations that we're gonna focus on. In fact, you're gonna be dealing with these things from now until basically you are done with any type of math, or to be honest with you, you kind of use them all the time. You just don't even know you're using them. So what we're gonna define here is going to be a function. A function is a relation that assigns to each element in its domain exactly one element in its range. Okay? So, more simplistically stated, a function is a relation where we see for every x value, there is one, I guess I read out the word, one, and only one y value. That's it. So if I give you an x, or if you give me an x, I will give you back a y value and only one y value. That is it. All right. So let's take the knowledge that we've gained and let's apply it to this question right here. Using the set of ordered pairs, all right, so using the set of ordered pairs, determine if we have a function. Now, in order for us to answer this, we need to go back to this definition right here, which is a function is a relation that assigns to each element in its domain exactly one element in its range. That exactly one is so important because it defines what a function really is. So here is going to be our very first example. So we have the ordered pairs -3, 27, -2, 8, -1, 1, 0, 0, 1, 1, 2, 8, and finally 3, 27. So a nice set of ordered pairs. To go about this, first thing we're going to do, and I'm just going to scroll up here a little bit. We're going to create like a little box. And we're going to label this our domain. We're going to do the same exact thing to the right. And we're going to call this our range. And we're going to map these points together. So, scanning from left to right, notice that all the x values are going to be -3, -2, -1, 0, 1, 2, and 3. My range is going to be 27, 8, 1, 0. And then if you look here, we have 1 again, 8 again, and then 27 again. So we don't have to rewrite them because they're already there. Now what I'm going to do is I'm going to map them. -3 points to 27. -2 points to 8. -1 points to 1. And then 0 points to 0. I'm going to keep going. 1 points to 1. 2 points to 8. And finally 3 points to 27. Now, if we go back and we think about what our definition is, so I'm going to scroll down. Our definition says a function is a relation that assigns to each element in its domain. So one element, one x value, you will get exactly one element in its range, or exactly one y value. So, as we look here, notice that, and I'm going to highlight as I move down. I'm going to highlight it in this nice green color so you know that's what I'm looking at. So if I look right here at -3, notice that it only points to one y value. That's it. Next, -2 only points to one y value. -1 only points to one y value. 0 only points to one y value. 1 only points to one y value. 2 only points to one y value. And finally, 3 only points to one y value. So, in this example, we have a function. And that is because for every x value, we get exactly one y value. Let me write that down. For every x value, we get exactly one y value. Even though the y values are repeated, the x values are only pointing to one y value. And that means everything for us. Okay? Now, let's do another example, because I think I showed you one here where we have a function. All right? I think it's going to be extremely beneficial if we show you one where it's not a function. So here's our next example. All right, we're going to do the same thing. We're going to have ordered pairs. Sorry, my dog barked in the background. So we have 9, -3, 4, -2, 1, -1, 0, 0, 1, 1, 4, 2, and 9, 3. So I'm going to do the same exact approach with this as I did previously. Create my sets, call it domain. Second one, we're going to call it the range. We're going to label the elements in each. So for my domain, looks like I get a 9, a 4, a 1, a 0, and then a 1, 4, 9 repeats. So I don't have to write them down twice. I got it right here. Now the range values are going to be -3, -2, -1, 0, 1, 2, and 3. All right, let's go ahead. Let's map them. -9. I'm sorry, not -9. +9 points to -3. 4 maps to negative 2. 1 maps to negative 1. 0 maps to 0. Then we have 1 maps to positive 1. 4 maps to 2. And then 9 maps to 3. Now, if you want, you can pause the video, take a guess on it whether or not this is a function. And if you unpause the video, you're going to learn that this is not a function. All right, now let's understand why. And I'm going to highlight the bad people here in this problem, and they're right here. 9, 4, and 1. And the reason why they're all bad, if you look at the number 9, for example, notice that the number 9 maps the negative 3, but it also maps to positive 3. And according to the definition, for every x, you get exactly 1 y. And this is where we violate, because this 9 points to 2 different y values. The same thing applies to the 4, and the same thing applies to the positive 1. So, as long as at least one of your elements in the domain violates the definition, you do not have a function. It's game over. Okay? Now, the next thing I'm going to do is I'm just going to show you another quick way that we can do this. Okay? And I'm just going to write, we can also determine functions using the vertical line test. All right, so let me show you how this works. All right, I'm going to go ahead and pull out a graphing utility. For me, I use Desmos. And I'm just going to go ahead and type in some equations right now. So I got, let's do 4x plus y equals, oh, sorry, I didn't realize my caps lock was on. 4x plus 3y equals negative 8. And what you're going to notice here, and I'm going to go ahead and just copy and paste this into our notes. So a nice Desmos picture here. All right, so what you notice here is that if I were to draw a vertical line in purple, so let's just say right here, little vertical line, all right? Notice that this vertical line intersects at that position right there. In fact, let me just move it over just a little bit so it's right there, so we can make this look really nice and pretty. Okay? Now, the reason why I'm doing this, everyone, is because when you look at this, this is going to be the point, -5, 4, but most importantly, you only touch your graph once. That's it. You only touch it once. And that does not violate the for every x value, you get exactly 1 y value. Okay, that's very important for us because that's what a function is. So just by doing the vertical line test, I can quickly determine if I have a function or not. Now, you do have to be careful because this is just one vertical line. But if you notice, I can come down here. There's another vertical line. I only hit my graph once. Down here, I only hit the graph once. Okay? Let me show you an example of where this fails. So we're going to go back to Desmos real quick. All right, we're going to turn off this graph, and we're going to graph another one here. Okay? So this is going to be x plus y to the second power equals 4. Or I'm sorry, 3. 3 is fine. Okay? So let's copy and paste this into our notes. And then let's do the vertical line test again. So now notice here, everyone. I'll use a different color this time. I'll use pink so it'll pop. You can really see it. If I were to draw a vertical line right here, okay, notice I end up getting two x values right there, okay? The first one, I guess we'll move it over. We'll make it look nice and pretty. We'll do here and here. So the first ordered pair is -1, comma 2, but then the other ordered pair is -1, comma -2. But look how this violates the definition. Notice that if I were just to do a quick little domain and range here, when a domain is -1, my range is going to be 2 and -2, and it points to two different y values. That is a direct violation. So this is not a function. So just to kind of sum things up real quick, if I just erase everything, the vertical line test says if you draw a vertical line and you hit your graph more than twice or two times or more, not a function. So the vertical line test tells us that if we touch our graph more than once, which in this example on the board right now, we clearly do that, we do not have a function. All right. Okay, so now we're going to move into what we call function notation. So we have an idea of what a function is. We have an idea of what they look like, and we even have tests on how to determine if we have a function. Now what we're saying is, if we do have a function, how do we write these things, and what can we do with them? So here's function notation right here. All right. For the function, we'll call it y equals f of x. Now, what this is telling me right here, all right, is that I'm going to have an expression of only x variables. That's what that tells me, okay? What we can say is f is the name of the function. X is in the domain. And then f of x is going to be our range. Now, sometimes we do refer to the domain values and the range values as these words right here, and you may have heard them before. We think of our domain as the independent variable, and then we think of our range as the dependent variable. Arthur, calm down. Now, there are two other names that I'm going to write, but I'll write them in parentheses because I do use them. The independent variable we think of as the input. The dependent variable we think of as the output. And you will see why I use this notation in this very first example here. So once we have a function, what we can do with them is we can evaluate them. So this example is going to be to evaluate the function. We'll call it f of x equals 3x to the second minus 2x plus 1, 4. f of 3, f of negative 1, and f of t. All right, now here's how we approach this. I'm gonna do this for this first example in each one, and then the next example, I'm not gonna write this out here because we should kind of have an idea of what to expect. All right, so let's pretend we have this special type of calculator, and it's called a function calculator. All right. Now, unfortunately for us, this calculator only knows how to do one thing. And what it knows how to do is f of x. And we have defined f of x as 3x to the second minus 2x plus 1. Okay? And what we're going to do is we're going to erase the variable x, and we're going to put parentheses there first. Now, the next thing we're going to do is we're going to take each one of these values. So for the first one here, this is read f of 3. All right, and what that means is the 3 is going to be what we let x equal, or another way to think about it would be this is going to be our independent variable, which is our input. So what we're going to do is we're going to input the number 3 into this calculator, and then as soon as we hit enter, the calculator is going to take that number, it's going to substitute it in, and then it's going to go ahead and crunch these numbers and give us what we like to call our output, or the dependent variable. So to evaluate this, and I'll do the math for us underneath. To evaluate this, 3 to the second is 9. 9 times 3 is 27, minus 6, plus 1. And 27 minus 6 is going to be 21. And then 21 plus 1 is 22. Now, here's what this really means. What we've just calculated, everybody. F of 3 equals 22. We've just calculated our very first ordered pair, because the input value is 3, which is our independent variable. And then it maps to the output value, or the dependent variable. So let me write that out here. So this is our input, or what we like to call the independent variable. Okay. Let me zoom out here just a little bit. And this thing right here, I'm going to highlight it in blue for us. This thing right here, 3x to the second minus 2x plus 1. That allows us to map 3, which is our input value, to 22, which is our output value, or, as we like to call it, the dependent variable. Okay? And that is how we do this. So I know I kind of took a long time showing everything, but I want to make sure that you understand exactly what's happening. This is so much more than just substituting in a number and then telling me what it equals. Okay? This is all about figuring out ordered pairs, because these things are related to each other. The input and the dependent variable are related to each other. Now, let's go ahead. I'm going to erase everything, and we're going to do f of negative 1. So I'm just going to erase everything here. All right, I guess I could have left that. We'll do this, put like a little comma there. All right. So f of negative 1. So put negative 1 into the calculator. It's going to substitute it in for us. Negative 1, negative 1. Negative 1 to the second power is positive 1. 3 times 1 is 3. Negative 2 times negative 1 is positive 2 plus 1. And 3 plus 2 is 5 plus 1 more is 6. So f of negative 1 equals positive 6. And there's our ordered pair right there. All right. Finally, and to be honest with you, this is the easiest one. We're going to go in and do f of t. Now, I know you're probably sitting there going, well, how is that easier? Now, I'm going to erase all this down here because I'm going to need a little bit more space. All right. We're going to put t into the calculator. Now, remember, the calculator is going to substitute that in. But here's the problem. We have no idea what t is. Neither does the calculator, but the calculator doesn't care. All it's going to output, and I'll write it in blue, is 3t to the second minus 2t plus 1. And our ordered pair is going to be t, comma, 3t to the second minus 2t plus 1. That's all it can do for us. All right? So if you can just understand this like little example here, you can evaluate any function that you want. All right? So let's try another one here. Let's evaluate g of x, which is equal to 4x minus 7, if, or how about this, if x equals 4 and x equals t minus 3. Okay? So here's what I'm really asking you to do. For part A, I'm asking you to evaluate g of 4. So g of 4 is going to equal 4. Write out the relation, write out 4, and instead of writing x, put parentheses, minus 7. Now remember, 4 is the input. So we're going to input it into our function, and then we're just going to go ahead and calculate what this is. 4 times 4 is 16, and 16 minus 7 is 9. So we have the ordered pair 4, 9. Pretty straightforward. For the next example, part B, I'm asking you to evaluate g of t minus 3. But once again, we approach this the same exact way. We put parentheses where the variable is. Then we make our substitution. And then all we have to do is simplify. I'm going to go ahead and distribute the 4 to give me 4t minus 12 minus 7. And then go ahead and group any like terms that I have. 4t minus 19. And yes, the ordered pair would look like this. T minus 3, comma, 4t minus 19. All right. So now, for this last example here, I'm just going to go ahead and do a word problem for us. So I'm just going to go right to our book. I'm going to steal a word problem out of the very end. So we'll just go ahead and do this one. All right, and we'll maximize this so we can all read it. And here we go. So the number, oh my gosh, I definitely have a lot of unread emails. The number of unread emails in Byron's account is 100. This number grows by 15 unread emails each day. The function n of t equals 100 plus 15t represents the relation between the number of emails n and the time t, measured in days. Part A is determine the independent and dependent variables, and then we're going to go ahead and find n of 7 and explain what this result means. So let's go ahead first and just rewrite the function. All right, so we have n of t equals 15t. Now, part A says determine the independent and the dependent variable. So this one is kind of not fair, but I'm going to explain something, and this is what we do all the time, especially in like a calculus course, all right? The independent variable, that's what I'm talking about right now. The independent variable is the one variable that we don't want to control at all. And sometimes we can't even control it. And time is one of those things in our life that we will never be able to control. So sometimes what we're really concerned with is how is the dependent variable being affected by the independent variable? Because one variable is going to depend upon the other. So in our example, the input is always going to be the independent variable. So our independent variable is equal to time. Now our dependent variable is going to be the output. All right, so after we calculate this, n of t is going to be the output variable. And that is going to be our dependent variable. And they are identifying the dependent variable as the number of emails. So there's part A. Part A is independent variable is time. Dependent variable is the number of emails. Part B, all they're really asking us to do is evaluate the number of emails when t equals 7 or 7 days. So how many emails does Brian have in his account after 7 days? All we have to do is take our input value, which is going to be 7, substitute it in, and then we go ahead and we solve. So we have 100 plus 15 times 7, which is 205. So we have the ordered pair, 7, 205, which we know is, after 7 days, Brian will have 205 unread emails. And that is what functions do for us. So I'll see you in the next video.